Hello everyone. Our next topic of discussion in thermodynamics is entropy. So we are going to have a fundamental concept about entropy. But before starting our discussion, let's make a little correction. Actually, this is not typing error. During the deliberation of the last lecture, that was lecture number 22, where the topic was refrigeration, by mistake I told that temperature increases from T1 to T2, but actually temperature decreases from T1 to T2 because T1 is greater than T2. So ignore that mistake. That is a deliberation error, not a typing error. So take into account that since temperature T1 is greater than temperature T2, so temperature increases from B to C during reversible adiabatic compression of the ideal gas. Okay, so let's now start our next lecture number 23, concept of entropy. From the second law, an important factor, Q by T. Q, what is Q? Q is the heat change and T is the temperature at which the heat change is taking place. So Q by T has been obtained. That gives the idea of entropy. Entropy is the degree of disorderness of the system, and its expression is the final mathematical form of the second law of thermodynamics. So since this is the heat change, so instead of that, and in the Carnot cycle we have seen that Q by T1 equals to Q prime by T2. That means Q by T, this parameter is constant. And from that mathematical implication, a new parameter in thermodynamics, entropy, has been introduced, and the expression of its change is written as ds equals to dq reversible by T. That means that this heat change Q, if it is reversible, then it may also be written as dq reversible. Okay, and the corresponding temperature, if it is T, then the ratio of these two is the change in entropy, where S is the symbol of entropy and ds is its change. Okay, so dq is the reversible heat change in the system at temperature T, and entropy is such a function which is not path dependent. It is a state function, and its change ds is definitely a perfect differential. Now let us prove that entropy is a state function and ds is a perfect differential. We have to start from the mathematical form of the first law of thermodynamics, which is dq equals to du minus w, and for a reversible process, instead of dq we can also write here dq reversible, and the expression of du can also be replaced by the expression in terms of Cv, which is du equals to Cv dt, and on the other hand minus w can also be replaced by the term pdv, where Cv is the heat capacity at constant volume, P is the pressure of the system, and dv is the volume change. That means mechanical work. And if both sides are divided by temperature T, then in the left hand side we get dq reversible by temperature T equals to, in the right hand side, Cv into dt by T, P into dv by T. Now this P by T can be replaced by R by V from the ideal gas equation for 1 mole, Pv equals to RT. So from there, instead of P by T we can also write R by V, and here dt by T can also be written as d ln T, because d ln T is equal to dt by T. On the other hand, here dv by V, this can also be written as d ln V, because d ln V is equal to dv by V. So we get the final expression dq by T equals to Cv d ln T plus R d ln V. Now if both sides are integrated by giving proper limits, then we can write from limit 1 state 1 to state 2 dq reversible by T equals to, in the right hand side, Cv is the constant, so it should be integration of d ln T from the limit state 1 has the temperature T1 and state 2 has the temperature T2, while R is the constant, so plus R into integration of d ln V by giving limits from V1 to V2. V1 is the initial volume of state 1 and V2 is the final volume of state 2. Hence the left hand side is actually integration of ds, which is nothing but equal to the change in entropy delta S. So let's see what is the final value of delta S, and from this integration we can conclude that the final value of delta S is nothing but Cv ln T2 by T1 plus R ln V2 by V1. So what we can conclude from this relationship of delta S? We can conclude that dq rev by T for a given change from state 1 to state 2 depends only on the states. That means only T1 and T2 and not on path by which T1 is transformed into T2 or P1 is transformed into P2. Therefore, dq reversible by T is a perfect differential. Conversely, ds is a perfect differential. So S is a state function. Now Clausius inequality. So if we are talking about dq reversible, that means heat change at reversible process for reversible process. Then what about heat change at irreversible process? So heat change in the definition of entropy involves reversible process. But if the heat change is irreversible in nature, then entropy change will be greater than the ratio dq rev by T. That is, ds must be greater than dq rev by T. Okay, so this inequality is known as the Clausius inequality. So that's all about the fundamental concepts of entropy. Thank you. Have a nice day.